Welcome to TBPi Academy, and in this video I'll be talking about chirality. So chirality is a concept in organic chemistry where you can basically have atoms that look nearly the same in how the atoms are connected, but the actual spatial geometry of them is different. So as an example, you can have two different molecules. So here's some molecular models. Now these molecules look the same. When you actually look at the atoms connecting them, you can see here we've got central carbon with an ethyl and methyl group, an oxygen, and a hydrogen on the back. So kind of these groups are the same, but looking at this other one, the groups are also the same, ethyl, methyl, hydroxy, hydrogen. But when you compare them, they're clearly different. In fact, they're mirror images of each other. So I'm going to show how we can distinguish these two molecules by how they are actually named. So I'm going to start by drawing the carbon chain of this molecule. So just like any other flat molecule, just draw lines between the bonds. Now we have to worry about what is coming into and out of the board. This oxygen is coming out of the board, so we can draw that as a wedge. So just kind of a wedge like that. Then we have to show that OH there. We technically have to fill those in. Usually I'm lazy and don't bother filling them in. And then the hydrogen is what's going to be going into the board. So we'll draw that as some dashed lines. So right at the same carbon, just like that, we have the hydrogen. For the other molecule that's a mirror image, we can start just same carbon chain as before. But now we notice that the hydrogen is actually coming into the board and the oxygen is into the board. So we'll draw hydrogen now as a wedge, and the OH is going to be a dash. So we can see here, these two molecules are mirror images of each other because the wedge and the dash of the OH and the hydrogen are switched between them. We could also draw this by keeping the OH and the hydrogen the same positions. So then just the hydrogen still has to be a wedge and the OH still has to be a dash, but switching those positions, those are equal to each other. We could also draw the mirror image by literally mirroring it on the paper, so flipping that carbon chain, drawing the OH still as a wedge, but now kind of in the opposite direction. So those are going to be the same molecules. So up in the top left, that's one molecule, and then all of these other structures are the same mirror image of that molecule. Now, it's kind of cumbersome to always call something the mirror image or exactly describe the structure, so we're going to be looking at assigning letters to these. So that'll be either R, S. So we have to look at where the actual chiral carbon is. So the chiral carbon is the carbon in the molecule that has 4 different groups coming off of it. So in this example, and we're just going to focus on, again, these two molecules, so I'll mark these here. So these two molecules are mirror images of each other. And in each of these, the chiral carbon is going to be right in the center there. We've got 4 different groups, the ethyl, methyl, hydroxy, and hydrogen. And the same goes in its mirror image. Those are both the chiral carbons. Say if we had something where instead we had like 2 OH groups, even though we have that wedge and that dash, this is actually not a chiral molecule because, again, that is only 3 different groups coming off, not 4. So now we have to look at what priority groups are coming off. So we could have priorities 1 through 4 for the 4 different groups. So priority 1 is kind of, I guess, the largest group. It basically has the largest weight to all of them. And this is determined by the fact that the atoms in the group are going to have the highest molecular weight. So it's not the whole group, but we'll talk about specifically, we'll look at certain atoms. So the lowest priority, priority 4, that's going to be the opposite. That'll basically be the smallest importance, so the lowest molecular weight. So once we've arranged these 4 priorities, then we can go ahead and assign whether a molecule is R or S. So in this molecule, looking at these, so again, just looking at this chiral carbon, we have to look at what atoms are connected to it. So those would be an oxygen here, hydrogen here, and then 2 carbons here. So just what's directly connected. So comparing all of these, we can see that the carbons, those have molecular weight of 12, and then oxygen has molecular weight of 16, hydrogen has 1, which is lowest, Sometimes, not in this molecule, but sometimes we'll see nitrogen that has molecular weight of 14. So looking at these molecular weights, we have to determine what has the highest priority of the atoms directly connected. So in this case, the oxygen is the one with molecular weight of 16 that is the highest, so we can go ahead and label that as 1 for priority 1. But now looking at what could be priority 2, we can see we've actually got 2 carbons directly connected, so we can't tell yet which of those will be priority 2, so we can go ahead and look for lowest priority. So hydrogen, if we've got that connected, that always will be the lowest priority, so we can label that as 4. Alright, so now we have to come back to these 2 carbons. So both of these atoms themselves have the same molecular weight. So now we have to compare what atoms are connected to them. So kind of as a tiebreaker. So here we've only got 3 hydrogens on this methyl group. But now this carbon has 2 hydrogens, but also another carbon connected. So to keep track of it, we could just label 3H for 3 hydrogens. Then over here, 2 hydrogens and then 1 carbon. So between those, the tiebreaker will go to the one on the left because of that carbon. So now we've determined this side is going to have higher priority. So then we can label this side as priority 2 because it has higher priority than the other side, so we can label that as 3. So now that we finally have all 4 of our priorities assigned, we can start worrying about whether this is R or S, which is the whole point of this. So kind of as a guideline, R is going to be going to the right in general. So kind of, you don't need to know Latin, but it literally means to the right. And then S is for sinister, which is to the left. So what do we mean by right and left? Well, if we're kind of looking at the top of a circle, going to the right would look like something where we're going clockwise. And in contrast, if we were going to the left, that would look like going anti-clockwise. So to determine the rotation, we're actually counting from priorities 1, 2, and 3. So whether that's going clockwise or anti-clockwise will determine which way we're going. And the other thing we have to worry about is which direction that lowest priority, priority 4, is going. So if we're going in the direction where it's into the board as a dash, then we are following this clockwise, anti-clockwise for R and S. So we could actually have one other case. So now where we're having the lowest priority come out of the board as a wedge, we'd actually have R as anti-clockwise. And likewise, we would have S as clockwise. So again, these are for when the lowest priority is a wedge coming out of the board. So back to this example, we do have the case where the lowest priority is going into the board. So we can follow along whether we're going clockwise or anti-clockwise. So let's go ahead and look at these priorities. So we had the OH as priority 1, so we can start by just having the tail there and then go to priority 2, which was that ethyl, and then end at 3, which was our methyl group. So we can see here we're going in that anti-clockwise direction, and we've got the hydrogen, the lowest priority, is into the board. So putting those two together, we're that bottom case. So this is an S for this chiral carbon. Alright, so as a summary of what we've covered, so chirality is assigning a letter to which direction a molecule goes. So we will either assign a molecule R or S for being quote-unquote right or left-handed. So R is going to be the case where we're going either clockwise and where we have the lowest priority as a wedge into the board, or when we have going anti-clockwise and the lowest priority is out of the board as a wedge. And then the opposite is S, where we go anti-clockwise with the lowest priority into the board, or if we're going clockwise with the lowest priority out of the board. And remember that for those clockwise or anti-clockwise, what we're doing is we're counting priorities 1, 2, and 3. And the other thing to keep in mind is just knowing what values for priorities. So just from the periodic table, we can look at priority of different atoms. So for oxygen, that'll be 16 as its molecular weight. Nitrogen is usually the next one with 14. Carbon will have 12. and hydrogen is usually, well, is going to be the lowest with 1. So thank y'all for watching this TBPi Academy video covering basic chirality.